Welcome to The Explainer. Today, we're embarking on a high-energy journey together through the literal fabric of our universe. We're going to take the raw, totally hyperactive elements of the periodic table and figure out exactly how they combine, shift, and bond to build the complex chemical societies that make up absolutely everything around us. Think about this for a quick second. What could a ripening banana sitting on your kitchen counter, a flawless diamond ring, and a bottle of nail polish remover possibly have in common? On the surface, absolutely nothing. But if we zoom all the way into the microscopic level, they are intimately connected by the brilliant underlying rules of chemistry. Understanding these rules basically unlocks the hidden mechanics of our everyday lives. Okay, let's dive into this. Here's our roadmap for today. First up, we'll meet the reactive metals. Second, carbon and its family. Third, the rules of attraction. Fourth, the hydrocarbon foundation. And finally, how functional groups add flavor. Section 1. Meet the reactive metals, looking specifically at Group 1A and 2A. Taking a look at the original lecture notes, the general properties of alkali metals, we're talking lithium, sodium, potassium, really reveal their hyperactive personalities. You see, they only have one single valence electron, and they are desperately eager to give it away. That makes them incredibly reactive. And if you check out their densities, they are shockingly light. Lithium, for example, has a density of just 0.53. It's actually so light that if you drop it in water, it literally floats right on top while violently reacting. Because these metals are so incredibly reactive, they put on an absolute show when you introduce them to energy. If you've ever watched a fireworks display and wondered where those brilliant colors come from, well, you're actually looking at alkali metal flame tests in action. When these metals get excited by heat, their electronic transitions give off vivid, signature colors. Lithium gives us this stunning crimson red. Sodium burns bright yellow. Potassium shines lilac. Rubidium flashes a deep red wine. And cesium burns a really cool blue-violet. It is abstract chemistry creating very tangible, real-world art. But that reactivity changes the moment we step just one column over to the right, to the alkaline earth metals, or Group 2A. While the alkaline metals we just looked at are soft enough to literally cut with a butter knife and melt at pretty low temperatures, the alkaline earth metals, like magnesium and calcium, are a lot more robust. They're harder, they're denser, they have much higher melting points, and while they're definitely still reactive, they are way less explosive than their Group 1A neighbors. Now, what's really interesting about this slide is the very last element on the list, radium. Beyond all the cold hard numbers for melting points and atomic radii, there's just a phenomenal human story here. Radium was discovered back in 1898 by Marie and Pierre Curie, and they painstakingly processed actual tons of residue from uranium mines just to extract a tiny fraction of a gram of this pure, highly radioactive metal. It's such a great reminder of the sheer human effort required to uncover these fundamental building blocks. Section 2. Carbon and its family, covering the Group 4A elements. If the periodic table were a high school, carbon would absolutely, hands down, be the social butterfly. Sitting right there in Group 4A, it has 4 valence electrons, which means it can form up to 4 covalent bonds. But what makes carbon a true game changer is its unmatched ability to bond with itself. It can form these incredibly long chains, branched structures, and complex rings. That one single characteristic makes carbon the essential foundation for all organic chemistry and, quite literally, all known life on Earth. To really appreciate carbon's versatility, you just have to look at its allotropes, which are different physical forms of the exact same element. On one hand, you have graphite. It's amorphous, soft enough to easily rub off on paper as pencil lead, and has a pretty low density. But on the other hand, you have diamond. Forged under insane extreme pressure deep in volcanic pipes, a diamond boasts an incredibly dense, compact structure. It is metastable, impossibly hard, and even transfers heat efficiently. It is just wild to think that the soft soot in a pencil and the hardest gemstone on a ring are built from the exact same atomic blocks. Section 3. The rules of attraction, diving into electronic theory. So the single most important rule in this entire playbook is electronegativity. Picture this as a molecular tug-of-war. When 2 different atoms form a covalent bond, they rarely share those electrons equally. One atom is almost always stronger or more electronegative and pulls the shared electrons closer to itself. This creates a polar bond, basically a slight electrical imbalance that entirely dictates exactly how that molecule is going to behave and react with everything around it. Another fascinating concept here is resonance. In some organic molecules, the electrons aren't just stuck in one place between two atoms. Instead, they're delocalized, meaning they kind of smear out and shift back and forth across the molecule. You can think of resonance as a molecular shock absorber. By spreading out that electron density over multiple bonds, the entire molecule becomes significantly more stable and resilient. In this crazy electronic dance, we basically have two main types of chemical actors. On one side, we have nucleophiles. These are our electron-rich species, packed with negative charge and actively looking for a nucleus to share it with. On the flip side, we have electrophiles. These guys are electron-poor, slightly positive, and desperately seeking electrons. Just like magnets, opposites attract, right? Chemical reactions are essentially just the electron-rich nucleophiles seeking out and attacking those electron-poor electrophiles. Section 4, the hydrocarbon foundation, focusing on alkanes, alkenes, and alkynes. So the crucial point is this really specific, testable fact centered around the number 4. When carbon atoms decide to form a double bond, like what we see in the alkene family, they are sharing exactly 4 electrons, meaning 2 pairs. This specific interaction creates one super strong head-on sigma bond and one parallel sideways overlapping pi bond. This localized density of 4 electrons creates a highly reactive site, making those double bonds a massive target for the electrophiles we just talked about. And hey, this isn't just textbook theory, this plays out in the real world every single day. Alkanes, which only have single bonds, are totally packed with energy. They are the natural gas heating your home and the LPG you fire up in your grill. Alkenes, with those double bonds we just mentioned, are more reactive. Ethene, for example, is literally a plant hormone used globally to trigger the ripening of fruit, which is exactly why your bananas turn yellow. And alkynes, featuring incredibly tight triple bonds, pack so much energy that burning acetylene creates a flame hot enough to slice straight through solid steel. Finally, Section 5, functional groups add flavor. A functional group is just a specific atom, or maybe a little cluster of atoms, that you attach to a hydrocarbon chain. But do not underestimate them. They are essentially chemical outfits. Just like putting a chef's hat on a person completely changes their role in a restaurant, attaching a hydroxyl group to a carbon chain completely changes its physical and chemical properties. That functional group totally dictates the entire chemical behavior of the compound. And this brilliantly illustrates the vast diversity of organic chemistry all in one place. It's basically your ultimate cheat sheet. Just by tweaking the oxygen and nitrogen arrangements, we get entirely different classes of compounds. Slap on an OH, it's an alcohol. An oxygen bridge, you've got an ether. A carbonyl flanked by carbons gives you a ketone, while an NH2 gives you an amine, which usually has that distinct, basic, fishy smell. Bringing this entire thing full circle, right back to our original hook, these functional groups are the secret ingredients in our daily lives. That aldehyde group gives us formaldehyde to preserve biological specimens. The ketone group gives us acetone, the exact solvent stripping off that nail polish. The alcohol group gives us the ethanol we use in our perfumes and fuels, and that carboxylic acid group, it creates acetic acid, which provides the unmistakable sour punch in your kitchen vinegar. As we wrap up this explainer, I want to leave you with this thought. We've seen how tiny shifts in electronegativity, or just sharing 4 electrons in a double bond, can completely redefine matter. If these simple, microscopic electron dances can turn a lethal gas into table salt, or ancient dead plant matter into a sparkling diamond, what other unseen chemical reactions are silently shaping the world around you right at this very second? Keep observing and keep exploring.